Futorny from the Southern University of Science and Technology, and he will talk about twisted localization in conformal field theory. So let us welcome our speaker.
Thank you very much. So it's a real pleasure to participate in this wonderful event. So in some sense, my talk will be a continuation of Tomoyuki Arakawa's talk yesterday, where he gave a description of geometric aspects of conformal field theory. And I will continue with some algebraic techniques in the representation theory of vertex algebras. So let me start just with this picture and this quote from Israel Moisevich Gelfand, who once said that mathematics is representation theory, right? Meaning the role of representation theory in our life. And so yesterday, Professor Frankel gave a beautiful overview, historic overview, and future perspectives of representation theory. And I'm going to add a few pieces that were missing in that picture related to the life beyond the category O. And all this relevant to conformal field theory. I don't need to say a lot today. After Tomoyuki Arakawa's talk, he described everything what was necessary. So the mathematical framework we have in the 2D conformal field theory, and this is taken care of by the vertex operator algebras. So here are the fathers of the vertex theory. Again, I will not talk much about that. I just put the formal definition for the sake of completeness. But I will skip that. So we know that maybe the main idea, the most essential ingredient is the concept of a field in this theory. And again, we saw this picture yesterday. So this is a 3D theory. There are two important pieces of the moduli spaces, Higgs branch and Coulomb branch. The geometric part of this, again, Tomoyuki described quite in details. So these are certain varieties, like Quiver variety here and Braverman-Hülkenberg-Nakajima variety on the right-hand side. And there is a connection. So if we start here, we can chiralize it, get the vertex algebra, and then we can take associate varieties. So we have this kind of going back and forth, and at least conjecturally we should get the same thing if we go at the end. What I want to say here, what was not mentioned yesterday, that there is a recent paper of Ben Webster where he showed that Coulomb branch has another algebraic structure, the so-called Galois, algebra of Galois order. So this is the concept that we introduced with Sergei Ovsienko around 2010. And so this is the family of associative algebras which have a certain invariant skew group structure. So it's a subalgebras in the sub-skew group algebra. Then there is a automorphism group acting on this skew group algebra and our given associative algebra. And in fact, it belongs to the invariants. And this concept was introduced to unify two things: enveloping algebra of GLM and generalized Weil algebra. Because in some sense, they were parallel representation theories with somewhat similar outcomes. And then the idea was to introduce a class of algebras which would include these two. And in fact, so Galois algebra is a kind of that. So which means if column branch, it has an associative algebra structure, is one of those, it means the whole this representation theory technique can be applied, and we can get a lot of information about that. Okay, so that's what I wanted to mention here. Passing to 4D again, we saw this map yesterday. So the map from 4D and n equals 2 to 2D theories, and there where we have VOAs at the end. Very recently, it was believed to be injective. So Tomoyuki explained why it is not surjective, right? Because of unitarity. But until recently, it was believed to be injective, but not anymore. So as we heard, it's a finite map. Right? Should be a finite map. And again, so the Higgs branch should correspond to the associative variety of the image vertex algebra on the right-hand side. Yeah, conjecturally again. Well, this is the sort of motivation for the whole story. Now I go to affine vertex algebras. So the affine Kac-Moody algebra, so here are the two giants on whose shoulders we stand, the fathers of the theory, and Victor Katz and Bob Moody. Bob Moody once told me that he never expected that the theory will kick off and will become such significant as it is now. So this is the loop algebra that Pengo already showed. The universal central extension is one-dimensional, this central element C, and it will be convenient also to use the degree derivation D. So the D brings an extra derivation, so it's an extra element of the Cartan subalgebra. Then we have the universal affine vertex algebra, right? So this is just a vacuum module, so induced from one-dimensional representation of the positive currents and with a fixed central charge K. Right, so that I will denote this way Vk, the universal affine vertex algebra. Okay, so variety today, even today, Pengo already reminded that this is just G star. Now, the concept of a smooth module. So there is a natural Z grading on our Lie algebra. And so I will use sometimes hat, sometimes tilde, depending if degree derivation is included. If I'm not mentioning the difference, then it's irrelevant. It holds for both. Yeah, so there's a natural Z grading by the degree of T. And the module is smooth if for any vector can be annihilated by sufficiently large currents, positive currents. And then the significance of smooth representations is because there is one-to-one correspondence between the reducible smooth representations of affine algebra and the affine vertex algebra. Right? So if we want to understand the representation theory of affine vertex algebra, so we just need to understand smooth representations of affine Kac-Moody algebra. And then the first problem that I would like to discuss is the state of the art in the smooth representations of our affine Kac-Moody algebras. So what are the examples? Well, the obvious examples are category all. So naturally everything there is smooth. The Whittaker modules. So Whittaker modules are those that are determined by a certain function on a positive part of the Cartan decomposition. Right? Cartan decomposition of our Lie algebra is negative part Cartan and positive part. So if we look at the homomorphism on the positive part to the field, that's a function that determines the Whittaker module. And if we mod out, so if we consider one-dimensional representation determined by this function, and we induce up, then we mod out the central character, just fix any central character, then the module will be irreducible, right? That's in the finite dimensional setting. Affine is more complicated, but the idea is the same, right? And the module is naturally smooth. Here's the family of smooth modules constructed by parabolic induction. So we start, I will use all the time this little p. It's a parabolic subalgebra of a finite dimensional underlying finite dimensional G. This is a Levy, right? So L, some reductive finite dimensional Lie algebra, and the radical U. And now I consider parabolic subalgebra of the affine algebra, where the Levy part, I keep my finite dimensional L and just add the rest of Cartan, whatever is missing. And then the radical of this algebra looks like that. And then I do parabolic induction, right? I take any module over L, properly extend it to the whole L hat, and just take in proper scalars here. In fact, N is a L hat module, not just L, but essentially it's an L module. Its simplicity determined by the L module structure. And then induced up. Right, so if I'm staying away from the critical level, I will have a unique simple quotient, which I denote by L. And so these are examples of smooth modules obtained by parabolic induction. There is another family, which I call mixed modules. So recently we obtained these modules with Xinxin Guo, Yao Hu Shu, and Kaimin Zhao. Why they are mixed? Because they combine two structures, a weight structure and a partial Whittaker structure. So the Whittaker structure is defined on the Heisenberg, positive Heisenberg part. That's we use the weight function, and on the positive part, which is not Heisenberg, we just define as 0 in the usual way, but not for the whole n plus part, but starting from a certain height. Right? And then it turns out that this way we can get lots of irreducible representations. They are modules for G hat, not for G tilde. We don't have a D action. D action can be introduced afterwards, just tensoring with polynomials in D, but then the resulting modules will be again simple, smooth modules, but D action is free, right? So we cannot get weight structure for D this way in this class of modules. But I'm not going to talk more about this. Now, Harishchandra modules. Harishchandra, so we have a Lie algebra with a Cartan subalgebra. Then the category of weight modules consists of those where Cartan subalgebra is diagonalizable. And the weight module is called Harishchandra if the weight space is a finite dimensional. And then I will denote it this way, the category of all Harishchandra modules for a pair A and H. So in particular, so those parabolic induced modules that we had above, so if we start with the Harishchandra module for finite dimensional G, we will get Harishchandra modules for G tilde, but not necessarily for G hat. So the degree derivation will give us finite dimensional multiplicities. Okay, so now I want to know what are the smooth Harishchandra G tilde modules. Okay, so this is an old result. So the classification is the following. So if we have a simple, so the first result, suppose we have a simple Harishchandra, not smooth, any simple Harishchandra module over G tilde with a non-zero central charge, then it will look like that. Right? And it is isomorphic to a module of this kind. So it's a parabolic induced for some non-trivial parabolic subalgebra. And it induced from something. This n, remember, this was a module, simple module over the Lévy subalgebra. So, and it must be cuspidal. It means that the root elements of L act injectively. It means if you start from any point of the module, it's a weight module, right? So it has weights. It's like a lattice. You pick a point and you start applying the root elements of L. You can go anywhere you want. You will never get zero. That's what it means to be cuspidal. And moreover, there is a restriction what kind of Lévy L we will have, because it's a reductive finite dimensional algebra, so it will be a direct sum of simple components plus some central part, and simple components are necessarily of type A and C. So this follows, historically there were two steps to get it. First is so-called Fernando-Futorny parabolic reduction. So the two cuspidal modules, that was first step, and then Fernando showed also that cuspidal modules exist only for type A and C if the algebra is simple. And this follows from the fact that the dimension of the closure of the minimal nilpotent coadjoint orbit coincides with is the Gelfand-Kirillov dimension of the enveloping algebra module of the annihilator. And by Gaber-Katz inequality, it's less or equal double Gelfand-Kirillov dimension of the cuspidal module, which is a double ring of the algebra. And since dimensions of the nilpotent orbits are known, just compare where it can happen. And it only can happen in A and C. And then it's just a matter of constructing cuspidal modules for A and C. And we know that for others, they don't exist. That's how it works. So this reduces classification of all simple Harish-Chandra modules to just to classification of cuspidal simple modules, which was done by Olivier Mathieu using the procedure called twisted localization. And the answer is that any such simple module is a subquotient of application of certain functor ds mu to a highest weight module with highest weight lambda. And then that's classification of all simple Harish-Chandra G tilde modules is done. And as a consequence, as a corollary, we have classification of all smooth modules, smooth Harish-Chandra modules, or the same simple Harish-Chandra modules for our universal affine vertex algebra. So they're necessarily positive energy, which means they have a boundary somewhere. And they can be induced, obtained from highest weight modular lambda by twisted localization. So the physicists add also a plus spectral flow. It means you can change the Borel subalgebra, but if we use subquotient, I mean, that can be replaced. But essentially, spectral flow means you consider L lambda not just for a fixed Borel subalgebra, but for all possible choices of Borel subalgebras. Okay, so then we have complete classification in the Harish-Chandra category. And then twisted localization, so now I will describe what it is. So this is a family of functors parameterized by two things: arbitrary real root alpha and any complex x. So now I'm defining it in the affine setting, right? The theorem was for finite dimensional, the Mathieu theorem, but we can define the same functors in the affine setting. And they preserve the smoothness. Smoothness, that's the significance. Right, so suppose we have fixed positive root alpha, arbitrary, take a third generator f alpha, and then consider the multiplicative set generated by this f alpha. Then we can do localization of the enveloping algebra. And then if we have any module M, we can localize this module. So then we obtain something else. That's the first step. That's what D stands for. But also, for any complex X, we can consider the following automorphism of the localized enveloping algebra, defined by this formula, and using the fact that F alpha is odd nilpotent, the sum is finite, so it is well defined. And we can use this automorphism to twist the module structure, to twist the action this way. Right? And that's what is D alpha X means. Oh, maybe I have it here. Yeah, and now suppose we have a set of commuting roots, S. So for each root, we choose a complex value xi, and then dsx, x is a tuple, means exactly, it's just a composition of functors that we describe. Okay, so this is a twisted localization. So these are very nice functors as they preserve the smoothness, so we can use them and given a module M, we can produce a new smooth module. And generically, we expect it to be simple again if we start with a simple module. Okay, so now I want to know if we can classify just simple smooth weight modules. Because remember, in the set of examples, I showed that there's lots of mixed possibilities. If we don't require, there could be this Whittaker stuff involved, so it's more complicated. Let's concentrate on weight and G tilde model. So with a degree derivation. So is it possible to classify them all? Well, at some point I had a conjecture using the Peng's phrase with 3 quotation marks. So I believe that it's true. Unfortunately, it's not. So I thought that, okay, if we apply, just take highest weight module and apply this bunch of functors like that, not always we will stay in the Harishchandra category, right? L lambda is in the Harishchandra category. But if we apply blindly these functors, we will go outside because the weight spaces will become infinite dimensional. And I thought it's good. So Matthew had to be careful how he chooses them. But I don't need to be careful. I just apply all possible. I will get weight modules, generically simple, smooth. So maybe that's all. Unfortunately, not. And it's quite easy to figure why not. So let's take this triangle decomposition of our G tilde, the standard one. And let's take any element in the enveloping algebra of the negative part, which is homogeneous, and which is odd nilpotent, right? So I don't want there to have imaginary part, right? Just the real roots. And then just take this element and do the same localization as we did for F alpha. So the difference is that F alpha was a root element, but now I don't require U to be a root element. It still works same way as before. Because it's odd nilpotent, we will have a well-defined functor and it will preserve smoothness. So if we apply it to a simple Verma, start with a simple Verma, apply this functor, and then we will get a simple module which is very wild. And so generically it will be simple and not isomorphic to the ones that we have from above. So it's sort of, unfortunately, conjecture is wrong, and the answer to the question is like that. So no matter how deep you dig a hole in the ice, you still have infinite ice in front. So there is no hope, at the moment, at least. On the other hand, there is another functor. You see this d alpha axis. It's a family of very powerful functors that work very well. Of course, I did not mention that x should not be integer. If x, this complex parameter, should not be integer because it would not give anything new. It should be a non-integer value. Well, so there's a very powerful family that provides more and more examples of smooth, simple modules, but they don't exhaust everything. On the other hand, there is this another functor. It's like a little cousin of that family. I like to think about it this way. Imagine the Brazilian national football team. You know, strong players, generally strong, not always, but general. And they play as just one body. But sometimes there are special players, different. It's years ago, there was a player with the name Garincha. Physically, he was a little bit different. I think his legs were not even, but he was extremely talented player and he could do the game himself. So this little functor is not like the brothers or sisters before, but he's extremely useful. And this is like digging a hole in the ice, you know, going straight in a line. And then he has many interesting properties. And so we call them twisting functor. So imagine that we have, in the case of SL2, imagine that we have a highest weight module, L lambda. So if we apply d alpha functor, then we just get a string with still no bridge going from lambda to lambda plus 2. That's a d alpha. Now, if we apply d alpha x, that's the same as doing this theta x automorphism applying here, then if x is not integer, we are building the bridge. So now we have a beautiful bridge between lambda and lambda plus 2. That's the story before. Now, this little fellow, if we apply it to L lambda, we get lowest weight module with lowest weight lambda plus 2. And then you can play with it, you can switch the action, twist the action and get back highest weight module. And that's what our Hippo functor does. But we don't do it, so T alpha is good enough for us. So let's look at the SL3 picture. So this is highest weight module with highest weight lambda. And then I have two simple rules, alpha and beta. So this is minus alpha direction, this is minus beta direction. So if I do T alpha, I will get this module. And you see I have a highest weight with respect to a different Borel. Yeah, if I do d alpha x, then it would give me SL2 string, irreducible SL2 string as a boundary. But now imagine, but here if I do T alpha, this is like a spectral flow. I go from this module to this module, then next I can, for example, do it with respect to this root, which is alpha plus beta, then I will get another highest weight module with respect to a different Borel. But look here, if I apply to this one, T alpha plus beta, so minus alpha minus beta is this root. Of course, I am assuming that the module is simple, or at least T alpha plus beta. Yeah, I'm assuming that Verma is simple for simplicity, because we need the action of F alpha to be injected in order to have a non-trivial image. So if I do localization with respect to this root, then the weight lattice will be the whole lattice. And every point will be infinite dimensional, even though we start with the usual Verma with finite dimensional spaces. This is so-called dense module, right? It has no holes. And generically, it will be simple. So this is the T alpha module. You see, it allows us to go from finite dimensional multiplicities to infinite dimensional multiplicities. And our recent result with Huimin Gao and Libor Krishka, so we look at the properties of these T alphas. So first of all, I will assume, so just for simplicity, apply it to a Verma module for the affine algebra, and I assume that this Verma module is simple. Again, for simplicity. So T alpha preserves, an alpha is any positive real, preserve the smoothness. We can control the simplicity. We know if M is simple, we know exactly when T alpha M is simple. So there is a criterion. And if it's not simple, then it has a finite length. So it's a very interesting property. When the image will be in a Harishchandra category, it's if and only if alpha is a simple root. If alpha is not a simple root, then we are outside of Harishchandra category, so the weight spaces are infinite dimensional. And if alpha is simple, as we saw in the pictures, this will be just the highest weight module for a different Borel. Now, when it is dense, you see, in the previous picture, we got the dense module when we applied it to Verma module for SL3. Of course, it's not always the case, right? But it will be dense. It means the weight lattice of this module will be everything, like a coset of H star by the root lattice. If and only if the root alpha in the decomposition with respect to a simple root contains all simple roots. Then we will get a dense module. If it is not the case, then the module will be bounded. There will be a hypersurface in the weight lattice which bounds the weights of this module. Okay, so this is the situation if we work with Verma modules. Let's look at the example of SL2. Right, so we have two simple roots, alpha and minus alpha plus imaginary delta. So I'm assuming that the Verma module is simple and isomorphic to the Wakimoto module, so I can take this realization, the Wakimoto realization of this highest weight module, and the action of Fn generators is just minus delta n on this space. So my module is just this space with a natural action of, of course I don't write the formulas for En and Hn, right, but they're more complicated, but Fn acts this way. So what happens if we apply T alpha? Alpha is a simple root. So then the image can be realized as this space. So where just delta 0 is switched with x0. Right? So if we continue, suppose we apply T alpha and then T beta, then we get one more here, x minus 1. So delta minus 1 will be switched with x minus 1. And you see, so we're just extending x's. And from the picture, remember when we had highest weight modules, so we're going from one highest weight module to another highest weight module with respect to a different Borel, and so on, if we keep applying to simple roots. Same here, this is like a spectral flow, reflection of the spectral flow here. But it will be quite different if we choose this real root, minus alpha plus 2 delta, and we apply directly to a Verma module. Then again, delta minus 2 will be switched with x minus 2. But you see, there is a break. There's nothing smooth here. I mean, there's no flow. We have deltas mixed with x's. And the resulting module is dense. That's exactly, it will be wild module with infinite dimensional weight spaces. It's still smooth, but it will be dense, yeah, outside of Harishchandra category. Okay, now to describe one more property of these modules, let's stay with the same parabolic subalgebra of finite dimensional G as before. And let's choose lambda to be L dominant. And choose F lambda to be a finite dimensional simple P module. So it's just a finite dimensional L module extended to a P module structured with a trivial action of U. Then we can consider induced module, right? This is the construction that we had before. And we can apply T alpha. So we'll denote the image this way, W P lambda alpha. And this module has an interesting property. So suppose alpha is a real root. So I just want to introduce this commutative subalgebra gamma alpha. So for a given real root alpha. So it is a commutative subalgebra of the enveloping algebra generated by Cartan and the Casimir element of the SL2 subalgebra based on alpha. Right, so just extended a little bit our Cartan subalgebra, just added Casimir element. Right, it's a polynomial algebra. And then, so suppose we choose alpha to be a root of, remember this was affinization of U here. So I don't want alpha to be a root of L because it doesn't make sense to apply T alpha to F lambda because it will kill it. Because we need an injective action, and F lambda is finite dimensional, nothing injective there. So F alpha is injective on this module, and it turns out that after the application of the functor T alpha, this module has, remember, it will be a dense module with infinite dimensional weight spaces, but it will have finite dimensional multiplicities with respect to gamma alpha. So you can picture the lattice with infinite dimensional Cartan multiplicities. And then the little Casimir of the root alpha preserves each weight space and it breaks it. It not necessarily has a simple spectrum. Not necessarily. Generically, yes, but not necessarily. It might have multiplicities, but they're finite. So each weight space will break into a direct sum of finite dimensional eigen subspaces with respect to Casimir. And it gets even better. So now you can imagine that we have any commutative subalgebra containing gamma alpha. As long as it contains Cartan and contains this Casimir, then it will have finite multiplicities on the whole model. And this has a flavor of a Gelf-Unsettling module in the finite dimensional setting. Right? There's no concept of a Gelf-Unsettling module for the affine setting, neither in the finite dimensional setting for outside of type A. There is no fixed concept of a Gelf-Unsettling module. But this one is a kind of analog of that. So we see that T alpha functors not only provide us new examples of simple smooth modules, but also have very nice features Now quickly, that was all discussion about the universal affine algebra. Now the simple one. So I'm interested in admissible rational case. Just recently, it's a curious fact, Dražen Adamović and Ivana Vukovara recently showed that they constructed a singular vector in the universal affine vertex algebra for D4 and for this central charge. And so if you print it, it will be like over 500 pages, and this single vector consists of 600 plus monomials. So you can imagine the complexity of the structure. Okay, so if we're interested in Harishchandra modules, again, the previous discussion can be applied here. They're all positive energy representations. They are parabolic induced from some representations of finite dimensional G, right? Then, so by the Jus functor, we have to choose some representations of G, and that's a tricky part. So if we know which representations of finite dimensional G to choose to be on the top of our module, then we know all of them. Peng already mentioned today that the highest weight modules were classified by Katz, Wakimoto, and Arakawa. So, for example, you see in category O, for D4 central charge -2, there are only 5 simple modules. But for that strange central charge, -14/3, it's already 405 such modules. For SL2, this is an old result of Adamović and Miloš, classification of such modules. And for SL3 in Harishchandra category with Tomoyuki and Ramirez, we have a description. And then passing to a general case, it is now called relaxed highest weight representations. So these are Harishchandra modules with a boundary. That's what it means. So if you stay within the category O and you just look at the admissible representations, this is not an interesting category, right? We get an interesting category if we drop the requirement to have the tip of the iceberg, which is our highest weight, but we can have any other boundary. The name is due to Alexei Semikhatov. Yeah, so it's an old name, and physicists like it, so it stays. So there are many contributions to the description of relaxed highest weight modules. Kawasetsu and Rideau provided an algorithm essentially based on the twisted localization that we described on the Matthews result, how to step by step obtain all of them. Right, so that's the situation with relaxed highest weight modules. My question is, okay, this is an algorithm. Okay, you can do it step by step, but is there any way to construct explicitly these representations, one way or the other? And that's what we were trying to do from different points of view. So one of them is the following. So let's start with the wild vertex algebra. So for every root alpha, we have a positive root, we have a beta gamma system. Then there is a Fagan-Frankel homomorphism from the VK vertex algebra to the tensor product of the wild vertex algebra and the vertex algebra of the Heisenberg. Okay, and then there is a commutative diagram. Okay, so here this is the Fagan-Frankel. This is the Zhu going to the finite part, right? From the universal affine, this is enveloping algebra. And here we get some wild algebra, A0 and enveloping algebra of the Cartan. So A0 corresponds to just drop put n equals 0. Then there is a homomorphism due to Krishka-Somberg from the enveloping algebra of finite dimensional G to this tensor product. There's a general formula. I'm not going to explain what it is, but that's the image of any element in a concise form like that. So here, this is the standard Cartan decomposition for G. F alpha is a standard basis, root basis for the negative part of the Cartan decomposition. X alphas are coordinate functions on n bar. A0 I already mentioned, that's the Weil algebra generated by X alphas and deltas for all positive roots. And so this formula describes homomorphism pi G, which is right here. So it makes this diagram commutative. Okay. In fact, there is affinization of this homomorphism. So if we now take the Weil algebra of infinite rank, right? So we have n. So I'm moving from the language of Weil vertex algebra to just Weil algebra. So just take this huge Weil algebra with many, many beta gamma systems. Then there is a homomorphism from the enveloping algebra of the affine G to the completed tensor product of this Weil algebra with the Heisenberg. And then, and this gives us a representation, right? When the derivative act in the usual way. And this will correspond to the first free field realization of the affine algebra, or it is also called imaginary Verma module. So it's not a standard Verma module, not a Vakimoto. It's because Vakimoto is the second free field realization. But this gives the first free field realization. But not in the language of the vertex algebra, but in the language of just homomorphism. And so this can be, there is a parabolic version of that, which gives parabolic first free field realization if we do the following. Let's take a different affinization over our parabolic subalgebra. This is our fixed parabolic subalgebra from the beginning of finite dimensional G. And now we take a different affinization this way. So the levy of the affine parabolic will look like that. So there's a loop algebra of L with central charge C, and similarly with the radical. And then if we start with any module over the loop algebra for L with a fixed central charge, allow U natural act freely, then we can consider the induced module. Right? This is a very strange module. It has a mixture of finite and infinite dimensional weight spaces. It's like this so-called imaginary Verma module. But it comes from this construction. I'm not going to use that. I want to play a different game. Because here I have an explicit, this is explicit homomorphism. So, and in this construction, derivatives acted as a derivative, as annihilating operators. But this is just a Weil algebra. I can take a different representation of the Weil algebra, and that's what I'm going to do. So let's take a natural triangle decomposition of the Weil algebra by the sign of n. Right? So all positive n's go to a plus, and negative n's go to n minus, and a0 is, remember, it's n0 case. Then we can take any module over a0, declare that a plus acts trivially, and induce up. So then the induced module I will denote like that. And then, so I use the homomorphism from the previous slide. So I have a representation of the Weil algebra. For the Heisenberg, I will take just a vacuum representation. And then I pull it back. And then I get a module over a affine algebra, which I denote it like that, W. And we call it the relaxed Wakimoto module. So this is sort of an analog of the classical Wakimoto module because it has a free field realization. And in the generic case, when it is simple and the induced module M is simple, then they will be isomorphic. And so that's the whole purpose, was to get a free field realization for these modules. And then ignoring the Heisenberg, so we can think of this as a functor from A0 representations to G hat representations. And in particular, we can recover the classical Wakimoto modules. Right? If we apply this functor to a Verma module, then the image will look like that, where W is identified with this space. And then if Verma and Wakimoto are simple, then it will be just Wakimoto module, exactly. So these relaxed Wakimoto modules are kind of a generalization of classical Wakimoto modules. And these functors, W functors, behave very nicely with respect to T alpha functor. So if alpha is a finite positive root, not arbitrary real root, but finite, then these functors commute. And it means that if we are, imagine that we are in the relaxed highest weight module, right? So we have a top part. There's a hypersurface that limits our weight lattice. So we can apply T alpha functor on the top part, and then we can apply W, and it's equivalent of applying first W and then T alpha. And then in particular, that was the goal, and that's what the outcome is. So suppose we have this localized module, right? Remember that this W is just T alpha applied to a Verma module. And then on the finite dimensional G, the top part is a module for finite dimensional G. This is the module for finite dimensional G. This functor is affinization, so we get a relaxed highest weight module for affine G. But then now using the permutation of the functor, so we go all the way here and we end up with this. And it means whenever we have this fancy W, it means we have a free field realization of something that has on the top part the module obtained by localization. So what we get is a free field realization of simple relaxed highest weight modules. And you see, we are no longer in the category of relaxed highest weight modules of Kawasetsu and Rideau, because they have, their modules are in Harishchandra category. We are beyond, right? So we are free. We go wherever it goes. And still, so we get simple modules, we get smooth modules, and in many cases, we get free field realizations. And thank you very much.
So time for questions.
I'm curious about how much of this you can extend to the quantum group case, say for quantum affine algebra, like the functor. Can you define them?
Definitely, you can extend to quantum affine algebra. Yes.
Also, this relation with Weil algebra. If there is something.
Yes, also with the relation to the Weil algebra. Yes, that's in the process. Yeah. But it's not quantum affine yet, it's just quantum. For the quantum group, yes, so it is possible to do it when we do it. But everything can be quantized. Almost everything, yeah.
Since quantum groups were mentioned, if you specialize Q to the root of unity in this universe of modules, what do you expect?
You mean if we look at the virtual construction of the quantum and you do specialization?
Let's say with divided powers.
Good question.
Okay, good, so it's not a stupid question.
No. Yeah, okay. I think I have not thought about it.
Okay, thank you.
So, any other questions? So, if you apply your program or algorithm to this L-2 case or the other case, can you obtain all the simple module together without the relaxed weight
module? For Harishchandra category, so we have to, first we fix in which category we want to do it, right? Harishchandra category, that's Kawasetsu Rido. They have algorithm that gives all such simple modules for, I mean, for admissible level. No, I think it doesn't matter which one, you can do it always. But these functors work outside of Harishchandra category, right? And we cannot get all of them, as I explained, right? It's not sufficient. T alphas gives a very nice family with nice properties of such smooth simple modules, but cannot give all of them.
Did Kawasaki redot program exhaust all the possible modules, relaxed modules in Harishchandra category?
I think so, yeah.
Okay, thank you. So, more questions? Okay, so if not, then let's thank our speaker again.